Today we're going to be finishing up section 3.6 talking about rational functions that have holes in them. Okay, we kind of operated under the premise for last class that our numerator and our denominator did not have any common factors. So what happens is when they have a common factor in the numerator and the denominator that would cancel out, we're left with a hole in the graph. So there's a special way to handle that hole when you have it, and that's what we're going to be dealing with today. Okay, so here's a couple that I want to go through and look at the examples of. You're asked to determine whether the graphs have holes, and if it does have a hole, to identify the location of the hole. So when we look at this function here, we have two polynomials, but they do have a common factor. Okay, so what happens is they're going to cancel and basically reduce down to being x plus 3 over x plus 2. Okay, but we don't lose the domain restriction that we had for this because x still cannot be 1. Okay, so when we look at that, it's going to change a couple things. The first thing it's going to change is it's going to change our x-intercept because we're not going to have an x-intercept at 1 because there's a hole there. We're going to only have our x-intercept at -3. So it's going to be -3, 0 instead of having both of those as x-intercepts. When we look at this as far as identifying where the hole is located, the hole is located at wherever the x is that corresponds with the factor that canceled out. So the hole is located at x equals 1. And the value for that hole, we're going to actually evaluate the function that's reduced. So evaluate the reduced function. And we're going to get 4/3. So we actually have a hole that's located at 1/4. So if we looked at the graph, there would be a hole located there. And we'll look at a sketch of it in just a minute. All right, if we move on over here, this one is not factored, so we would need to factor it. Okay, so when we look at this one, we have no common factors, so there is no hole on this one. Over here, again, it's not factored, so we're going to need to factor this. Okay, this time we do have common factors that cancel out and reduce down. So the way that that changes this is our x-intercept is going to only be at 1, not at the -2, and our hole is going to be located at x equals -2. So we're going to find the y-coordinate by plugging into this reduced function here. So if I find f of -2, that's going to be -2 minus 1 over -2 plus 5. So that's going to be -3/3 or -1. So that tells me the hole is going to be at -2, -1. Okay, so let's take a look at how all this comes together. So on this one here, like I said, go ahead and factor. So this is going to factor x plus 4 and x plus 2. And then here we're going to have x plus 2 and x minus 1. So we have these common factors that cancel out. So when I go to work with this, I am going to have a hole that I need to identify. My x-intercept is going to be affected. So the x-intercept, we go and look at the numerator. But we don't get one here where it's canceled. So we're only going to have a -4. So it's going to be -4, 0 for my x-intercept. For my y-intercept, we find it the same as we always did. We're going to plug in f of 0, plug in 0 for f, and we're going to get 8 over -2, which will be -4. So I'm going to have a y-intercept of 0, -4. Okay, my domain I'm still going to get from the denominator because x can still not be -2 and it cannot be 1. So if I set this denominator equal to 0, then I'm going to get x is not negative 2, and x is not 1. The range we'll come back to with the calculator. My vertical asymptote, because these canceled out, there's a hole there and not an asymptote. So the only asymptote I'm going to have, only vertical asymptote, is going to come from this x minus 1. So I'm going to get x equals 1 for the vertical asymptote. The horizontal asymptote is going to be the same as it was before. These are same degrees, so we look at the ratio here. So this is going to be y equals 1. So I'm going to put all this together. I've got -4, 0, and I've got 0, -4. I have a vertical asymptote at 1. Have a horizontal asymptote at 1 as well. Okay. So I need to look at the whole. We said the whole comes from the factors that cancel out. So I have a whole at -2. So what I'm going to do is I'm going to plug in -2 into the reduced function. So my reduced function is going to be the x plus 4 over x minus 1. So if I plug -2 into that, I'm going to get 2 over -3. So I'm going to have -2/3. So my whole is at -2 and -2, -2/3. So instead of plotting a point there, I'm actually going to draw an open circle to indicate a hole in my graph. From here, I'm just going to complete my okay, so I'm going to plot these points here. So -5 is going to go here. -3 is going to be somewhere here. -1 is going to be at -1.5. 2 is going to be up here at 6. So when I connect these, what I'm going to do is I'm going to connect them just like I did before, except I'm going to have that open circle there. Try to connect them in as smooth a way as possible. This pen just does not allow for a very steady graph. All right, so we have a graph that looks like this. The main thing is we want to see this open circle here to indicate that that's where the hole is located. Up here, we've got a graph that's doing something like this for the shape of it. So our range on this one is going to be from -infinity to 1, and then from 1 to infinity, because 1 is where our horizontal asymptote was. So it gets close to that value, but it doesn't touch that value, and therefore we need to exclude it as part of the range. So I've placed this equation in our calculator. So I wanted to show you kind of what this graph is going to look like. So here's the graph. It hopefully looks a lot like what we had indicated, except the graph on the calculator is not going to show the holes. So this one had a hole located in there, and we need to still be able to see that. So if you go to the table, what you're going to see is that you have an error at 1. You also have an error at -2. So if we go back and look at the graph, clearly we can see this horizontal asymptote here at 1. So over here at -2, the way that we're able to identify there's a hole there is by looking and seeing that it is undefined on our table at that location. So that's how a hole is going to show up on your graph. If we were to use our trace key and trace over, what you would see is that as it gets close to -2, if we were to actually type in -2, then you're going to see that it doesn't give us a y value, and therefore it's undefined at -2 because there's a hole there. So I have two that I want us to look at here. This first one, if I factor the denominator, then what happens is these two are going to cancel. So my reduced function is going to be 1 over x. So if I'm looking at any domain restrictions, I still go back to here before I ever canceled anything out. So my x is going to be all x such that x is not 0 and x is also not 3. My vertical asymptote on this one is only going to be the one that didn't get canceled. So my vertical asymptote is going to be 0 and my hole is going to be located at x equals 3. Okay, so if I go back to the reduced one, that's the one you want to plug it back into. Then if I plug 3 into that, I'm going to get 1/3. So the hole is actually going to be occurring at 3 1/3. If we look at the graph for that one, this is the graph here. So you can see over here at 3 and positive 1/3, that's where we have the open circle to indicate the hole. We still have the vertical asymptote at 0. Okay, so for the next one, if we look at this one, we could take out an x squared from the numerator. So we're going to end up with x minus 2's that cancel. So this is going to be reduced down to an x squared. So for my domain on this one, my domain is still going to be x cannot be 2. So even though this reduced one is just a parabola, and it's a quadratic function, so there would be no restrictions, we still have to maintain the restriction that we had on the original function here. So x would not be 2. As far as vertical asymptotes go, we have no vertical asymptotes because we don't have a denominator on this. We do have a hole. That hole comes from the canceled factors. So our hole is going to be at 2, and then plug 2 into this, so at 2, 4. Okay, because this is our reduced. So when we put this in our calculator here, we can see that we're going to put parentheses around it. Look at the graph, and it's just a graph of a regular parabola. We have no vertical asymptotes whatsoever. But if we look at the table, we are still going to see an undefined value here at 2. And so that's what that's where the hole is occurring at, is here over here at 2. So our location that we identified was 2, 4. Okay, so here at 2, 4, we would have a hole that would be showing up. If we were drawing this out on paper, we need to put an open circle there. Okay, so this function here is one that I would like for us to practice with. Try this one to identify any intercepts, asymptotes, domain, range, any holes, and then finally sketch the graph. So the first thing we would need to do is to factor this. Okay, so we can see that these are going to cancel out, and we're going to be left with a reduced function that is x plus 4 over x plus 1. So as far as the intercepts, my x-intercept, I'm going to set this numerator equal to 0. I'm going to get x equals -4. So my intercept would be -4 and 0. My y-intercept, I'm going to plug 0 in, and so I'm going to get, when I plug 0 in, I'm going to get -12. If I plug 0 into that, the denominator here, I'm going to get -3. So I'm going to have 4. So it's going to be 0, 4. So I can plot those points, -4, 0, and 0, 4. For the asymptotes, my vertical asymptote is going to come from the denominator, but it's not going to come from the factor that cancels out, just from the one that's left. So if I set that equal to 0, then my vertical asymptote is x equals -1. So at -1, I'm going to draw a dotted line to indicate there is a vertical asymptote there. The horizontal asymptote, we look at the degrees. Here the degrees are equal, so I'm going to use the value in front, the coefficients, the ratio of the coefficients. So that's going to be 1 over 1 or 1. So y equals 1 is going to be my horizontal asymptote. Okay, for the domain, we actually look back before anything cancels. So the domain is going to be all real numbers except 3 and -1. Those are the two numbers that will make the denominator be 0, and we can't have a division by 0. We're going to come back to the range after we get our graph, but we do need to look at the wholes. Okay, so the wholes are always going to come from a factor that has canceled off. So my whole is going to be at 3. So I need to evaluate my function, the reduced function, at 3. So that's going to be 3 plus 4 over 3 plus 1. So 7 over 4. So my whole is going to be at 3 and 7/4. So if I come over here to 3 and 7/4, is going to be somewhere in here. So that's an open circle. Okay. All right, so from here we can just fill in some points and kind of sketch the graph. So when we do that, we're going to get a graph that looks something like this. It gets close to our asymptotes, goes through these designated points, and is going to look like this. Again, these should be smooth curves that get closer and closer to the asymptotes. And we have a vertical asymptote here at -1, and then we have our undefined whole at 3. So as far as the range goes, we do have to exclude this horizontal asymptote because it never touches that. So our range, I'm just going to write it up here, is from -infinity to 1, and then from 1 to infinity. So usually if you're going to have to exclude your range, it's going to be around your asymptote here. There are some other different situations where you may have to adjust it, but a lot of times it's going to be simply just excluding the asymptote. If you have that third part and it crosses the asymptote, then you don't really have to exclude anything. Okay, so that takes us to the end of section 3.6. So if you have any questions about rational functions or their graphs, please contact me and let me help you with this. Hope you have a good day.